Hi, everybody. So we're really close to that part where biochemistry really starts merging with medicine, and we start chemically engineering various polypeptide protein sequences to address specific receptors, etc. So in order to do that, we got to build up the larger protein. And we saw before that we have these triplets or codons of messenger RNA sequence that are all coding for various amino acids. And it's repetitive in that you might have one amino acid, like here we have glycine or alanine here, and it's got 1, 2, 3, 4 codon triplets that all code for it. So from an evolutionary perspective, these are the triplets that have minimized the amount of base pair mutations, allowing for all 4 of these to still code for alanine. We can think of the codon normally with respect to the messenger RNA. Here, obviously, they're looking at the DNA codon because they have GCT, but we know that the messenger RNA codon, in that case, if it were GCT, would be CGA. Okay, and if we had something here like GCA, that would be CGU. Remember that there is no thymine in messenger RNA. Okay, so we have all these amino acids. Okay, 20 amino acids. We have about 64 different codons, and that greater number of codon is really a protective thing. Thinking about that from an evolutionary perspective. So what we want to start doing right now is we want to start bringing these amino acids together. Remember, a protein is nothing more than a string of amino acids. So in this video, we're going to talk about how they actually connect. So when you saw these amino acids, we saw that the amino acids had always had a carboxylic acid on one side, and they always had an amine group on the other side. And that structure is where the name amino acid comes from. But then they also have these other things hanging off. And those things that are hanging off tend to always be hanging off in between that carboxylic group, a carboxylic acid group, and that amine group, where we have that amine group right here, and we have that carboxylic acid group right here. And that actually is a hallmark with respect to how amino acids differ to make different proteins. So let's zoom in here on. Okay, so first of all, let's just give you that format. Instead of looking at let's take serine right here, for example. Instead of looking at it in this skeletal structure, we're going to look at the amino acid in a very, very clear organic chemical structure format, where we're going to put the amine group on one side, and we're going to put the carboxylic group on the other side. And I'm not going to be drawing the skeletal structure here. So if we take serine here, for example, let's look at it in a very orderly, structured way. Okay, so we have the amine group on one side, that N, H, H. Okay, remember there's lone pairs here on that N. Okay, and then here, so that's that, we have this C. Okay, and what's coming off that C right here is this group. Okay. And that group is a CH2. And an OH. I'm just going to draw the OH like that. Okay, so that's a sort of an alcohol functional group coming off that. And then we have this other H here. Okay, and then we have the carboxylic acid portion. And it's also important to remember that there would be lone pairs here, and we'd have lone pairs here, and we'd have lone pairs here, and we'd have lone pairs here. Okay. So this amino acid here that you're looking at has a carboxylic group right here, that's this. Okay. It's got an amine group here, that's this. And then it's got this thing hanging off of that center carbon. And all amino acids are exactly the same, except for that thing that's hanging off the center carbon. Okay, so let's do a general look at how we talk about an amino acid. So we talk about an amino acid in terms of the left side, the center carbon, and the right side. Now, this left side and this right side never change, ever. It's always an amine group on one side and a carboxylic group on the other. We saw in the case of proline, that was kind of weird. These were connected, actually. So this side, we call this the N-terminus. Okay? Meaning that is the terminating side of the left side, which has the nitrogen. Okay? And this side over here, we call this the C-terminus. So all amino acids are actually these three carbon or these three atom molecules where you have an N-terminus, you have this middle carbon region, and you have this C-terminus right here. So all amino acids look exactly the same, but they differ based on what is hanging off of that C-terminus. And we call that the R group of the amino acids. So all amino acids are the same. They just differ based on their R group. Okay, so let's take a deeper look at those R groups and how those come together. But this is a very, very important thing for you to see. And notice, we couldn't have done this unless we really dived into organic chemistry initially. So let's take a look at some molecules. Here we have tyrosine. So let's draw tyrosine in the way that I did it up here, where we have the N-terminus, the C-terminus, and we really look at the difference in that R group. Remember, that's really how life becomes life, right? It's that R group. The difference in those R groups really affect the way the long polypeptide comes together. Okay, so we have the N side. Okay, we have NH. Okay, so that's that right there. That's connected to a carbon right here, which has an H coming off it. Okay, and then that's connected to that carboxylic acid group right here. Okay. So then what's coming off it? Okay, well, let's draw that. What's coming off that is a CH. Did that there. And then what's coming off it is this large benzene ring. Now, to make yourself, to make your life a little bit easier here, we can just draw the benzene ring, you know, the way it is right there. And we have that OH. So this here, this is the R group for tyrosine. And when a piece of DNA codes for an R group in tyrosine, we know that that's going to somehow, the accumulated effect of that, really indicate and affect that function of that protein. Here we have serine, and those are the codons, by the way. Remember, that's TAT, so that would be AUA, and TAC, that would be AUG, if we're thinking about DNA to messenger RNA. So let's do serine here. Let's look at it. These are different amino acids, remember, that would come together to form a larger protein. It's going to have a specific structure. I keep saying that. So let's do the N-terminus here. NH. Okay, that's that side. Connected to a C. There it is. There's our C. Connected to the C-terminus. Okay, the C-terminus, by the way, is that C, not that C. And what's coming off it that makes it serine and not tyrosine is a CH2 group. And that hydroxyl OH group that we saw earlier. So this now is the R group for serine. Okay, and now glycine, which is the simplest of all amino acids, has a really cool R group. And by the way, here are all the DNA codons, probably a lot of evolutionary mutations for glycine, which is why there's kind of this accountability system. It could mutate to any one of those and you'd still get glycine. And if you still got glycine, you don't have a mutation in terms of the functional protein that's produced. So and that's really cool, actually. You can have a mutation where T and C get replaced in the DNA, but not have a mutation in the protein itself, which is a really interesting thing to think about. Okay, so here, this one's drawn a little bit differently. We have the N-terminus on the left side already for us. So nice of you. And then we have the C here. And you notice, in this case, what is coming off of, let's draw the C-terminus first. So in this case, the R group is an H. There it is right there. Okay, so in summary, glycine only differs from serine, and serine only differs from tyrosine based on those R groups. Okay, well, these are individual amino acids. Let's make a really small protein based on these amino acids. Let's show you how those come together. Okay, so we're going to make a 3-peptide protein. So this protein is going to be made out of tyrosine, okay, and that's going to be connected to serine, and that's going to be connected to glycine. So this is going to be a protein. Obviously, this protein came from the DNA, which came from the messenger RNA, which made the protein, and that's the central dogma of biochemistry, remember. So we have this larger protein that we are going to make, okay? So different amino acids come together to make a protein. But another word for a protein is polypeptide. And the reason we're calling it a polypeptide is this bond right here, the bond that's ultimately going to link all of these together, which we haven't shown up here. That bond is called a peptide bond. Peptide bond. Peptide bond. Okay? So we have a peptide bond. So what does that peptide bond look like? Well, hint, we were only getting the carboxyl group before from last time at the C-terminus and the amino group on the N-terminus, and some people are getting alcohols, but now we're going to get an amide. And you probably are already seeing how that's going to happen here. So we're going to show the amino acid that gets formed between all of these, okay? And I'm going to do that for you right now, and that's something you guys are going to be doing, okay? So we're going to start with tyrosine, okay, the Y there. So N, H, H, okay. C, H, okay. And we have the R group on tyrosine, which we know. And I'm going to draw the organic skeletal structures here just to make it a little bit faster. So I'm going to go C, H2, well, not skeletal structures, but I'm just going to abbreviate it a little bit. We have OH. Okay. So now we have tyrosine right there because it's got that R group. Okay. So now what's going to happen here, okay, is the carboxylic group on tyrosine, this carboxylic group, is now going to do a reaction with the amine group on serine. Okay? So here we have tyrosine, and now we're going to bring in serine. And that reaction is going to form our peptide bond right here, where now the amine group on serine we're going to have serine's R group there. That's going to be the R group. The amine group on serine and the carboxyl group on tyrosine came together here, and this is your peptide bond. I want you to write that down, peptide bond. So you see, you lost a little bit of the C-terminus and you lost a little bit of the N-terminus right there. But we got to finish this friend off. And if this is serine, well, what is the R group on serine? That's that CH2OH friend right there. CH2OH. Okay. And now we have one more peptide bond that needs to happen between serine and glycine. Okay, so what's going to happen here is just like we saw up here, the carboxyl group on serine and the amine group on glycine are going to go there and form a peptide bond. Go away, low battery power. You're fine. Okay, so now that's going to bring glycine into the mix. So what's going to happen here is we're going to get another peptide bond. There's the amine or N-terminus of glycine. And there's the C-terminus. And because the protein is now over, we see the full C-terminus here, and we see the R group on glycine. Okay, and now we have another peptide bond right there. So notice the peptide bond has the amide functional group in it. The amide functional group is really the secret of biochemistry. So now, initially, when you had one amino acid, you had a N-terminus and a C-terminus with an R group. Now, we have a protein, which is a polypeptide. Normally, there's hundreds of proteins that make a large structure. But you see here now, we now have a large protein, and we have the N-terminus of the polypeptide protein itself on one side, and then we have the C-terminus here. So with all three of the various R groups. So that is how you draw a polypeptide. You take the C-terminus of one amino acid and the N-terminus of another, okay? And this is actually a reaction that loses water like we saw before in a lot of them. And we get these polypeptide bonds, which are amide bonds. You could probably imagine right now that these R groups are what determine the structure, the overall structure of the protein. So hope you followed along nicely with me there. Thank you. Please jump into the office hours if you have any questions.